In this section, we're going to talk about limits and continuity for multivariate functions. Now, I want to start with talking about continuity. And before we jump into what's going on with multivariate functions, let's quickly review the idea of continuity for single variable functions. Okay, so just intuitively, continuity means there's no breaks, there's no gaps, there's no holes in our function, right? So something let's do continuous first. So we could have something like this, right? Or maybe something like this. These are continuous functions, all right? There are no break or gap or holes in either of these functions. Notice sharp points are okay if we're just looking at continuity. The function wouldn't be differentiable here. We couldn't take the derivative at that point, but it is continuous. Okay? Whereas a function is discontinuous at a point if there is a break or a gap or an asymptote. Okay? So for example, maybe I have some function and there's an asymptote in the middle of them. Okay? It's discontinuous where the asymptote is. Okay? Or maybe I have a hole or a break entirely. All right. So these are all examples of discontinuity. Now I want to emphasize that technically these functions are discontinuous only at a single point. Only at the point where the break is the function discontinuous. In these other regions, the function's nice and continuous. All right. So it's the same idea. We're going to take this idea and apply it to a multivariable setting, and that's the idea of continuity. So let's look at what this would mean for a multivariate setting now. So if I'm in 3 dimensions, and let me just give you a couple of examples of discontinuous functions. I'm actually going to not write the axes. I think they'll just get in the way in this particular instance. So if I have some surface, okay, there's my surface. Now, right now, that surface is nice and continuous, right? There are no breaks, no gaps, no tears. Nice and continuous surface. Okay, but by just adding a single hole, now at that point, at where this hole is, the function would be discontinuous, right? Or I could have like a tear in the function. Okay, so maybe I have part of the function down here, and then up here I have the rest of the function. Okay, these are examples of how we could have discontinuity in a multivariate setting. All right. Now, there is one important concept that we usually skip over in Calculus 1, but it's an important idea. Why do we care? Why do we care if a function is continuous or discontinuous? So continuity helps us with approximating values, which is a really important thing to do in real life, right? I'm 5'8", right? That's how tall I am. But am I exactly 5'8"? No, I'm about 5'8". If I got a more careful ruler and looked at it more carefully, then maybe I'm 5'8" and 3/10 of an inch. or maybe I'm a little lower. Maybe I'm 5'7" and 9/10 of an inch, right? And if I keep on using a rule that was a little bit more exact, I could keep on getting closer and closer and closer. But the approximation 5'8" is a good approximation because someone who's 5'8" and someone who's 5'7" and 9/10 of an inch, there's not a whole lot of difference between them, right? And that's what continuity does. Height is continuous. If my height grows a little bit, then I'm just changing a little bit, right? It's not like I grow a 1/10 of an inch and all of a sudden I'm in a completely different category, right? Now I can go into the NBA and play, be a world-class basketball player. That's not how it works, right? A little change in height means you're just a little taller, right? It's not like in this example, if I go a little bit more this way, right? If I go a little bit more this way, all of a sudden I jump up. Continuity is all about the ability to approximate. So if I know my x value is somewhere around here, then I know my y value would also be around the right value. Okay, that's what continuity is. As long as you're close enough, you can approximate the right answer. That's the power of continuity, and that's why we care. It's a really, really important property that we use almost unconsciously in everyday life. Okay, anytime you make a measurement, you are unconsciously making an approximation. And that approximation only matters because what you're measuring has a continuousness to it. The approximation is good enough. Okay? All right, so let's take a look at an example. So here we want to determine the region in the xy plane over which this multivariate function is continuous. Okay? So there are generally only a few places where a function can be discontinuous. Usually what we're looking for is areas that could be problems with a function like this. All right. So places where we usually have discontinuity would be like zeros in the denominator. Okay. We might have problems if we have negatives under an even root. Another common issue is special functions. Now sine and cosine, they're continuous everywhere. But functions like natural log and tangent, secant, cosecant, cotangent, they all have discontinuities. And so we need to look for where the function might be discontinuous and then rule that out, and then everything else is continuous. All right. So in this particular case, I have g of xy equals natural log of x squared plus y squared. Now x squared plus y squared, that's not going to be a problem. That the inside of the natural log function, that's fine. The x squared and y squared, that's continuous everywhere, right? No zeros in the denominator, no special functions, no roots, right? But once we look outside of that, we say, oh, okay, we're dealing with a natural log function. The natural log function does have some places where it's only continuous in a particular region, okay? So in order to understand where this is going to be continuous, we need to understand where just the natural log function is continuous. Where is it defined? Where is its domain? Okay, so let's look at just the plain natural log function. Let's make sure we understand that. Let's see, I don't know if I want to use x and y just because we're using x and y here, and it wouldn't be the same x and y. So maybe I'll call my dependent variable t. All right, and I want to know what the function natural log of t looks like. What's the graph of natural log of t? So if you recall, the graph of natural log of t, you have a vertical asymptote along the vertical axis, okay, at t equals 0. And we approach that as t approaches 0 from the right. And then as t increases, we get something like this. All right. Notice in particular, it only works Natural log function is only defined where t is greater than 0. But as long as t is greater than 0, the function is continuous, right? So g of xy equals natural log of x squared plus y squared is continuous whenever what we plug into the natural log function is greater than 0, right? That's what we know about the natural log function. As long as what we're plugging in is greater than 0, we're good. So we need x squared plus y squared to be greater than 0, and strictly greater than, not greater than or equal to, right? We have that asymptote right at 0. We can't actually reach 0. The function is not defined at 0, right? So what does this look like? Well, in this particular case, there is only one value where we would be equal to 0. Normally with a inequality like this, you would want to first sketch the boundary. Okay? So I'd want to sketch x squared plus y squared equals 0. But because x squared plus y squared is always non-negative, the only way that this equals 0 is if x and y are both equal to 0. Right? So if x and y are both equal to 0, that would be this point right here, the origin. Okay? So the only solution is xy equals 0, 0. Now that's the boundary. That's where it equals 0. And we don't want to include the boundary. So this point is not in the domain. But for every other xy point other than 0, 0, this inequality will be true, right? Because I'm taking something squared, I'm adding it to something squared. So something non-negative plus something non-negative will result in something non-negative. Okay? It will be positive unless x and y are both equal to 0. So our region, if we draw it out, and usually for a problem like this, determine the region in the xy plane over which the function is continuous, the best way is to sketch out the region in which you are working. So here we're looking at this from above. Okay, so we're looking at the xy plane, we're looking down the positive z-axis. Okay, we've got a hole at 0, 0 because that's where x squared plus y squared equals 0, and we know we can't equal 0. But everywhere else, what we're plugging into the natural log function is going to be defined, no problem, right? Because it'll be greater than 0. So the only point of discontinuity is at the origin for this function. Okay? And I want you to see what's going on here. It always helps to see. So we have the natural log of x squared plus y squared. That's our function. Okay? And that's what we get. And so what we did is we took a look down the xy plane here, and we saw that the only point of discontinuity is at the origin. Okay, is that point 0, 0. It just keeps on going down and down and down and down. We never reach it. Okay, everywhere else it's continuous. It's just that point at the origin that's discontinuous. Okay, so it's that picture from above. That's what we're drawing here. That's what this is. Okay, we've got that hole at the origin, and everywhere else the function is nice and continuous. All right, let's look at just one more example. Here we want to determine the region in the xy plane over which the function 1 over xy is continuous. So our approach is the same. We're going to start by looking at where the function is not continuous. What could be a problem here? All right. So generally that means 0 in the denominator, negatives under an even root could be a problem, and then special functions. The only one of those that we have to worry about here is getting a 0 in the denominator. So we need to make sure that the x and y values that we're interested in aren't going to give us a 0 in the denominator, right? And then as long as we do that, we'll be continuous everywhere else, okay? Because polynomials are just continuous by default. If we just multiply x and y together, any product of x and y, adding them together, it'll be continuous, okay? And then a fraction of polynomials is continuous so long as the denominator is not 0. The denominator equaling 0 is really the only place we have to worry about, right? Otherwise, functions are usually continuous. All right. So we want to make sure so it will be discontinuous when xy equals 0. Okay. Well, when is x times y equal to 0? So we can use the zero product property, which says that if we multiply two things and we get 0, one of those two things has to be 0. So either x has to be 0 or y has to be 0. If either of these things happen, then my denominator is going to be 0 and the function will be discontinuous. So x equals 0 and y equals 0 are going to be two places that I want to rule out. Okay, so if I again take that overhead view, so I'm looking down the positive z-axis from overhead, looking at just the xy plane, what are the x and y values that I can plug in that will allow this function to be continuous? So I'm going to rule out the values that are discontinuous. So anywhere where x is 0, so I want to rule out x equals 0, and I want to rule out y equals 0. And I think I drew that the wrong way. This is x equals 0, and this is y equals 0. But anywhere else is going to be okay. So all of this area, that's going to be continuous. Okay, there are no problems there. I'm trying to decide the best way to do this. There we go. We'll do it that way. All of this area, no problems there. The only two places where I have problems are where x is equal to 0 and y equals 0. Everywhere else, the function is going to be defined and it's going to be continuous. All right. So this is my answer. All right. Let's see what that looks like when we put it into the calculator. Let's see if it matches. So our function is 1 over xy. And indeed, we already have the overhead view here. And you can see that the x-axis and the y-axis, the function isn't defined. There does seem to be a gap in the middle, doesn't there? That's just because the function doesn't reach that far. If you could allow it to keep going by zooming out, you'll get a more complete picture. It's just on those axes that it's discontinuous. Okay? Now, with continuity out of the way, let's talk about limit. And again, I want to start by thinking about limits in the single variable case, and then we'll extend those ideas to the multivariable case. So the idea of a limit is a function that is almost continuous. If you just tweak the function a little bit, plug the hole, move something around, then it will be continuous. Okay, something, for example, like this, right? Let me add axes. So if I have A here, if this guy is L here, then we would say that the limit as x approaches A of my function f of x equals L. What does that mean? That means as x gets close to A, then the y value is getting closer and closer to L. The function value, the point that it spits out, is getting closer and closer to L. Okay? The idea here is that it's almost continuous. If we could just plug the point, then it would be continuous. That's what a limit is. Okay, it's something that's almost continuous. We are approximating something as we get closer. It just happens that the thing we're approximating isn't necessarily equal to the function value at the point. It could be, but it doesn't have to be. Right? Compare that to something like this. Okay. What would we say the limit as x approaches a of the function is in this case? Okay, well, in this case, the limit does not exist, right? It's not a simple issue of just plugging a hole and then it's continuous. Even if I were to draw a point here, the function's not continuous, right? Because as I approach from the left side, I'm approaching one value. I'm approaching one value, okay? But as I approach from the other side, I'm approaching some other value. And that's a really important idea. In order for a limit to exist, we have to be able to approach from either direction and approach the same value. Okay? And we're going to see that that idea is going to play a major role in the multivariate case. So let's think about how this looks in the multivariate case. So the idea is essentially the same. Okay? I have some function and we'll say this function is z equals f of xy, right? And I want to approach some point. Okay, maybe it's a hole in the surface. And so I want to know if I let x and y both approach that value. Okay, so let's say the point is at x naught, y naught. So if we look at the limit as x and y both approach that, the x and y values of the point, then we say the limit equals L if as we get close, the function value approaches that limiting value L. Okay? Now I could give you a careful definition of limits. In single variable calculus, we talked about the epsilon delta proofs. If you want to look at that, it's in the textbook, but at this stage of your education, it's going to be more important that you have an intuition on how these limits work. And the intuition here is as we approach the x and y value, as x approaches x naught and as y approaches y naught, then the function value gets closer and closer to this value L. Okay. Notice that there are lots of directions we can come in. That's different from the single variable case. In the single variable case, I could go from the left, I could come from the right. Two directions, and that's it. In the multivariable case, I have a lot more ways that I can approach this point, right? I can approach it this way, and 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 this way. There's so many ways, right? Infinitely many ways. The limit only exists if I am approaching the value from every direction along every path. So in order for the full limit to exist, in order for the limit to be L, I have to approach L no matter how I approach this point. No matter how x and y approach x naught, y naught. Let's take a look at an example. So here we want to evaluate some multivariable limit if it's possible. Okay, so we have the limit as x comma y approaches 0 comma 0 of x squared over x squared plus y squared. Okay. Now, in order for this limit to exist, it needs to exist and agree as we approach 0, 0 from every possible direction. So taking that overhead view again, looking down the positive z-axis, just the xy plane, here is the point 0, 0. No matter how I approach it, if the limit's going to exist, it needs to exist and agree from every direction. So a great way to show that a limit doesn't exist is to find two directions where the limit does not agree. All right, and that's often a good strategy to start with when dealing with a problem like this. So what I'm going to do is I'm going to start looking in a few different directions. Okay, so specifically, I'm going to look in the direction down the y-axis. Okay, that's along the line x equals 0. And then I'll look in the direction down the x-axis. That's down the line y equals 0. Okay? By looking at only one path at a time, we can change a multivariable limit into a single variable limit. Okay? So let's look along the path x equals 0. So I'm going to fix x to be 0, and I'm only going to let the y change. Okay? I'm looking on this path right here. Okay, so x is going to be 0. So if I'm approaching 0, 0, x is already there. I don't have to worry about it. The only variable I have to worry about is I got to make sure y gets to 0. Okay, so I'm setting x already equal to 0, and I'm just letting y be 0. I'm letting y approach 0. If x is already 0, what does that mean for our function? Well, since I'm fixing x at 0, since it's not changing, I could plug in 0 for the x. Okay, but y has to stay y because I'm looking at the limit as y gets closer to 0. I want to know what happens as we get close. Okay. In this case, 0 over 0 plus something that's not 0 is 0. Okay. By the way, I know y is not 0 because I'm thinking about what happens as y gets close to 0. It's important to remember that for limits, you don't care what's happening at the point. I don't care what the function is doing at 0, 0. I care what the function is doing as I get close to 0, 0. That's what a limit is. What is the behavior of this function as we get close? Not what's happening right there, but as we get close. So if y is close to 0, that means y isn't 0. Okay, so 0 over something not 0 is 0. So this limit is 0. As I approach in this direction, okay, along this path, I get 0. Okay, now let's look in the other direction. Let's look in the direction y equals 0. Okay, so now I'm fixing y to be 0, and I'm going to let the x change. I'm going to let the x approach 0. Okay, so x squared over x squared plus y squared becomes x squared over x squared plus 0 squared. Since the x is changing, I want to make sure I leave that as a variable. But the y I've set fixed equal to 0 because that's the path I'm looking on. Okay? And you could see pretty quickly that the x squared plus 0 squared is just x squared, and then the x squareds will cancel. I'll get 1. All right? Which means the limit along this path is 0, and as I approach along this path, y equals 0, I get 1. the limits do not agree, the limits along these two paths do not agree, so the full limit as xy approaches 0, 0 of x squared over x squared plus y squared does not exist. Okay? It'll help if we can see this in our graphing calculator. So let's pull up our graphing calculator. Okay? Now our function was x squared divided by x squared plus y squared. Okay? And actually that green color is probably pretty good. So you can see what's going on at the origin. There is something funky going on there at the origin, isn't there? Okay, so what we did is we looked at this function along different paths. We looked along the path what x equals 0 down the, there we go, down the y-axis. Okay, you could see that this path, as we get closer and closer to the origin, it's just staying at this level, isn't it? Let me take that out. As we get closer and closer to the origin, along this path, we're just going to 0. That's what we got. When x is 0, we approach 0. Okay? And then the other path, when we set y equal to 0, so let's do maybe orange. Okay? Notice with this one, as we approach the origin, we have a higher value. Okay? We're going to 1, not 0. And you can see as the two paths approach each other, their function value, their z value, does not approach each other. Okay? The orange path would be along y equals 0, we're approaching 1. The z value of 1. Okay, it's higher up. The purple path here along x equals 0, that's this one, and it approaches 0 as x and y approach the origin. Okay? Let's take a look at another example. This problem is quite similar to the one we just looked at, but instead of x squared in the numerator, we have xy. Okay? So again, a good place to start is see if the limit exists along every way we can approach 0, 0. Okay? If we're looking along just one path, that limits us to a single variable. And we're good at taking single variable limits. Okay? So I always like to start with the path along x equals 0, which would be down the y-axis. So we're going to let the y value change. The x is already at 0. Okay, so we get x, sorry, let's plug in the 0 for the x. 0 for x times the y over 0 squared plus y squared. And we could see pretty much immediately that this is going to be 0, right? 0 times whatever y is will be 0 in the numerator. 0 over something not 0 is 0. Okay? So along that one path, along the y-axis, we get 0. Now let's look along the x-axis. Down the x-axis, y has a fixed value of 0. So if we're going down the x-axis, we're letting the x change, and we are interested in letting the x get closer to 0, but we're going to set the y already equal to 0. So we would get x times our y, which we fixed at 0, divided by x squared plus our y squared, which would be 0 squared. Pretty much the same thing as what we just dealt with, right? X times 0 would be 0 in the numerator, and then we get something not 0 in the denominator, because x is going to just be close to 0, not 0 itself. If it was 0, we'd have problems, right? 0 over 0 is an indeterminate form. That'd require more work. But 0 0 over something not 0 is 0. Okay? So, hey, look, we in two directions, our limits agree. Does that mean the full limit has to be 0? So remember, in order for a limit to exist, it's not enough to just check two directions. The limit has to exist and agree along every path in every direction. We've just looked in two. Okay? We've just looked down the y-axis, that's x equals 0. And down the x-axis, that's y equals 0. Okay, but we have a lot more ways that we can approach that origin, right? We can approach it this way, or this way, or this way, this way. There's lots of ways we can do this. What I like to do at this point is think about the line y equals mx and leave m as an unknown for now. Okay? I look along this line. Any line y equals mx will go through the point that we're interested in, which in this case is 0, 0, the origin. But by making a relationship between x and y, it reduces our problem to one variable. So I only have to think about what happens as x approaches 0. Because if x approaches 0 and y is equal to mx, then y will also approach 0, won't it? So I'm going to have x times y, so x times mx for some slope n that I haven't decided on yet. Okay, it lets me look in every direction instead of just focusing on one particular value of m, one particular slope. Divided by x squared plus y squared, and again, y is mx. Okay? So looking in this direction, let's just tidy up a little bit, simplify as much as we can. Right now, of course, if I just plug in 0, I get 0 over 0. That's an indeterminate form. So let's see if we could clean things up a little bit. In the numerator, I get mx squared. In the denominator, I have x squared plus m squared x squared. And I notice in the denominator, I could pull out the common x squared. So let's pull it out. Leaves me with 1 plus m squared. Okay? And now I can cancel the x squareds, and that's a big deal. Because those x squareds is what was giving me 0 over 0. That was giving me the indeterminate form. Now that those are gone, now I don't have an indeterminate form. Now I could just plug in 0 for all the x's. I don't have any x's left, but if I did, I could plug it in for all the x's, and I would just get m over 1 plus m squared. Okay, that is the limit. For any slope m, that's what I get. Okay, now we need to check. Does this agree with these limits I've already found? Well, no. Pretty much any slope other than slope 0, this is going to be a non-zero number, right? If m is 1, I'd get what? 1 over 2. I'd get a half, right? For any non-zero value of m here, for any non-zero slope, my limit isn't going to be 0. And so because it doesn't agree with these two, that must mean that the limit does not exist. So you could see why it's important to check every direction here. Okay? So our final answer here is that the limit for this guy, the limit as xy approaches 0, 0 of x times y over x squared plus y squared does not exist. Okay? And as usual, it's helpful to see what the heck is going on here if we look at a particular graph. So we have xy over x squared plus y squared. Just change a few things here. Okay, it's pretty much the same surface we were dealing with In the previous example, it's just rotated a bit. Okay? Now, the first two paths we looked at were the path x equals 0. Okay? And you could see that along this path, along the y-axis, we do indeed approach a z value, a function value of 0. Right? As we approach the origin. And then the other one we looked at was along the path y equals 0, along the x-axis. And we get the same thing. It approaches the origin. But we could see that those are kind of exceptional, aren't they? So more generally, we looked along the path y equals mx. And what we noticed was for different values of m, and it's behaving a little strangely right at the origin, but for different values of m, we hit that z value higher or lower. Right? Very rarely do we hit exactly at 0. So notice generally is not going through right at 0 unless I'm straight down the x-axis, in which case m is equal to 0. We usually are hitting that z value higher or lower. The limits do not agree. Let's take a look at another example here. And this example is going to be especially interesting. Now I want to start using the same approach we have done, where the limit is as xy approaches 0, 0. So let's start by looking at this along different paths. Okay, how are different ways that we could approach that origin? So I'm going to start the way I usually do. Let's start with x equals 0. Let's look down the y-axis. So we'll take the limit as y approaches 0 with x already there. And x squared times y over x to the 4th plus y squared becomes 0 squared y divided by 0 to the 4th plus y squared down this path. And that's 0. Okay? Real easy to see that that limit is 0. Let's look down the x-axis at y equal to 0. Let the x change and approach 0. So now I'm fixing the y at 0, so the function becomes x squared times y equals to 0 over x to the 4th plus y squared, where y is 0. And again, very quickly we can see this limit's going to be 0. The numerator is 0, the denominator will not be 0, with x just being close to 0, and so the limit goes to 0. Okay? So far everything agrees. But as we said, those are just two ways we could approach the origin 0, 0. Let's look generally at any line that goes through the origin. Okay, any other line going through the origin would have the form y equals mx. Okay, so if we look down any line of the form y equals mx with some slope m, we get the limit as, now I'm just going to worry about what happens as x goes to 0, because as long as x goes to 0, the y will go to 0 too, of x squared times y, which is mx along this path, divided by x to the 4th plus the y squared, which is again mx along this path. Okay, so just a little algebra here. Limit as x approaches 0, I get mx cubed on top divided by x to the 4th plus m squared x squared. I can factor out a common x squared from the denominator and cancel it with the numerator. So mx cubed over, factor out that common x squared, leaves me with x squared plus m squared. Okay, and I can cancel these two x's with two of these x's. limit as x approaches 0. My numerator is now just mx. I'm dividing by x squared plus m squared. And now, at this point, I could just plug in 0 because I have canceled the thing that was giving me problems, right? I couldn't just plug in 0 here because if I just plugged in 0 here, I'd get 0 over 0. 0 over 0 is an indeterminate form, okay? It means I have more work to do to find the limit. But now that these are canceled, this was the thing that was giving me 0 in the denominator, which means I won't get 0 over 0 when I plug in 0 for x anymore. Now if I plug in 0 for x, I get m times 0 over 0 squared plus m squared, which will be just 0. Okay, so the limit from every direction exists and agrees, right? They're all 0. So we have to be really careful here. This is I purposely chose this problem because it is a tricky problem. It looks like the limit should be 0. From every direction, we're approaching 0. Okay? The trick here is that the limit has to agree as we approach the origin from every direction along every path. We've looked at lots of paths that approach the origin. Okay? We've looked down the y-axis, the x-axis. We've looked every straight line that approaches it, but we haven't looked at every possible path. For example, I haven't looked at this path. Okay, that approaches the origin. I didn't look down it though. In order for the limit to exist, it needs to exist and agree in every direction along every path. Now, this is a rare example where you will have the limit not exist along a nonlinear path. Okay, not agree along a nonlinear path. So specifically, let's look along the path where y equals x squared. Okay, so again, if y is equal to x squared, that makes a relationship between x and y, and we only have to consider what happens as x approaches 0. Because if x is approaching 0 and this relationship holds, then y approaches 0 also. Okay, and so I have what? X squared y over x to the 4th plus y squared. So x squared y, where y is x squared, divided by x to the 4th plus y squared, and y is x squared. So there's my y, and that y is squared. Okay, and you could probably already see what's going to happen. I get x to the 4th on top, I get x to the 4th plus x to the 4th on bottom, which means on bottom I get 2x to the 4th, right? Those x to the 4ths I can cancel. With the x's gone, the limit is just 1/2. Specifically, not 0, right? There is a path that exists that approaches the origin where the limit is not 0. Which means the limit does not exist. In order for the limit to exist, the limit has to agree along every path in every direction. We found a path where it does not agree. So that means this full limit x squared y over x squared x to the 4th plus y squared does not exist. Okay. Now, how did I know to plug in y equals x squared? Well, it's because I carefully chose this example so that we get something that wasn't 0 when we approach along that path. I do not expect you in this class to look at this and immediately go, oh, I know what the problem is. If we approach along y equals x squared, that's going to give us some other value. No, it's very hard to look at this and know that that's going to happen. Okay, this example is not to show you really how to solve this. I didn't show you why I thought y equals x squared was a good approach, right? I knew it was a good approach because this is kind of a classic example of why just approaching a point linearly is not sufficient. Okay? But I do not expect you to be able to solve this problem without some help. If I gave you a problem like this, I'd say make sure you check this other path too. Okay? If I'm expecting you to look down a nonlinear path, I will give you some sort of hint on how to do that. All right? Let's go ahead and take a look at this in Desmos. Let me pull the graphing calculator over here. And our particular function is x squared y divided by x to the fourth plus y squared. Okay. And you could almost see the indentations of parabolas, can't you? Okay. So what we did is we took a look at this. We looked down the path x equals 0. We got 0. Okay. We looked down the path y equals 0. The limit was also 0 once we reached the origin. Okay. And then we looked down the path y equals mx for some value of m. Okay. And you can see that the path curves a little bit more. It's not just a straight line like these other paths are down the x-axis, down the y-axis. Goes up and down a little bit, right? But it does get back to the origin. Let me hide the surface for a moment. You can really see what's going on there. Okay? So no matter what m is, sometimes it scrunches up quite a bit, but it always gets back to the origin. Okay? So along every line, we're going through the origin. But it's just along this path y equals x squared that we can really see that, wait a second, something different's happening here. As we approach the origin, we're not going to 0. We're approaching 1. See how it stays up higher? Just along that path. It just sits atop that ridge. And it stays atop that ridge. But any line will eventually come off that ridge. Okay, and that's why the line always goes to 0. Even if I try to really get close to the edge, it eventually comes down because that ridge has the shape of a parabola. So the same technique that we're learning here about looking at a limit along different paths, it works for 3 variables also. So let me do an example with that just so we can see what's going on here. Okay, so here we have the limit as x, y, and z all approach 0 of x squared minus y squared minus z squared over x squared plus y squared minus c squared. So just as a check, we could look along different paths. Okay. Now, the idea of a path is we want to only let one of the variables change, and the other ones are either 0 or dependent on that one changing variable. Okay? So here, let's let x be the one that changes. Let's look along y and z both equal to 0. Okay, so I'm going to set y and z both 0, so that means the only variable that I'm interested in seeing change is x. And it helps if I actually plug in the zeros, doesn't it? Let's so we get x squared on top minus the y squared, which I've set equal to 0, minus z squared, which I've set equal to 0, all over x squared plus the y squared, I've set equal to 0, minus the z squared, also set equal to 0. The x squareds will cancel. It's real easy to see this limit's 1. okay, along that path. If this limit has to exist, it has to equal 1 along every possible path. So I can show that it doesn't exist by just finding one more path where the limit is not equal to 1. If there exists one path out there, any path where the limit isn't 1, then the full limit does not exist. Okay? So I've set y equal to 0 and z equals 0. What happens if I now let the y change? What happens if I let x equal to 0 and z equal to 0? And I'll only think about what happens as my y changes, as my y gets close to 0 along that line where x and z are both 0. Okay? So this limit, I get 0 squared minus y squared minus 0 squared divided by 0 squared plus y squared minus 0 squared. I get negative y squared divided by positive y squared. That's equal to negative 1. Which means that the limit does not exist. I have two different paths, both approaching 0, 0, 0, but I get two different limiting values, which means the full limit does not exist. Every example we've looked at so far, the limit has not existed. There's been some path that the limit along that path did not agree with the limit on some of the other paths, right? What happens if the limit does exist, though? So if the limit does exist, the method of paths that we were looking at, it's not great for proving that a limit does exist. It's really effective at finding two paths where the limit does not agree, and so proving that the limit does not exist. And it can give some intuition on why a limit might exist, but it's not great on its own at showing that a multivariable limit does exist. Okay, so let's start off with this simple example, and I'll tell you right now the limit does exist here. In fact, let's look along separate paths to show that the limit that most of the paths agree, that the paths we check agree. Okay, so I'm going to fix the x value. Now notice the x and y are approaching to -1. So I don't want to fix the x value at 0 like I have been doing. Every other example we've looked at so far, x and y have approached 0, 0. But now we're approaching to -1, so I want to make sure x is fixed so that it will actually go through that point to -1. So I'm going to set x equal to 2 and look at what happens as y changes and approaches -1. Okay? So I get 2 squared over 2 squared plus -1 squared, plus y squared. Right? If I just plug in -1, I don't get anything like 0 over 0. There's no indeterminate form here. So I could just plug in, and I get, what, 4 over 5, 4/5. Okay? That's because this function is continuous in y. At least at the point we're looking at. It's continuous when y is -1. And when a function is continuous, the limit value equals the actual function value. So I could just plug in. That's usually the way we approach limits analytically, by the way, is we use algebra to rearrange it or to cancel things. So I end up with an equivalent function that's equivalent everywhere around the point and continuous at the point. And we'll see more of that later. Okay? But this one's nice and continuous, so I can just plug in. Let's look along the path where I fix the y value. Again, be careful. I'm not approaching 0, 0, so I want to let y be -1, and I'm going to let x approach 2. Okay? So I get x squared over x squared plus my fixed y value of -1 squared. Okay? Just as before, there's no problem with me just plugging in 2. I don't get an indeterminate form like 0 over 0 or infinity over infinity. If I just plug in 2 for x, I again get 4/5. So far, everything's working out. Okay? And in fact, if I look along every possible path every possible line going through the point 2, -1. And you got to be careful here because it's not just going to be y equals mx, right? I need to make sure I go through the point 2, -1. So my slope is m, but I'm going to shift the line over so it goes through 2 and shift it up so it goes through y equals -1. So that is the relationship I want between y and x, right? No matter what the slope is, I will go through the point 2, -1. If x is 2, 2 minus 2 is 0, all of that goes away, and the y would be -1. Okay? So I only have to think about what happens as the x changes, as the x approaches to 2, because we saw as x gets close to 2, y is going to get close to -1. And so I have x squared over x squared plus my y squared, where my y is defined by the relationship m times x minus 2 minus 1 squared. Okay, it looks like a mess. It's not that bad because, again, if I just plug in 2, I don't get an indeterminate form. I don't get 0 over 0. I don't get infinity over infinity, nothing like that. So I can just plug in 2 to evaluate the limit. It is continuous when x is 2. Okay, so we do have to be a little bit more careful here. There's a little bit more going on. So 2 squared on top, 2 squared on bottom, plus m times 2 minus 2 minus 1 squared. Okay, 2 squared on top, that's 4. And on bottom, this 2 squared is 4. And here, 2 minus 2 is 0, times the m is 0. So all of this goes to 0. I just have the -1 squared. -1 squared is 1. I get 4/5. Okay, so it looks like from every direction that I've checked, I'm getting 4/5. Now we know that there are still infinitely many ways I can approach the point 2, -1. I do not have to approach in a line. I can approach with a parabola or a cubic function or some weird sine wave. There's all kinds of ways I can approach this. Okay, but it looks like the limit exists just based on what we have here. So let's take a look at the full limit. We get limit as x comma y approaches 2 comma -1 of x squared over x squared plus y squared. Now, just like for each of these, what did I do to find each of these limits? I just plugged in, right? Guess there's only 3 here. I just plugged in. I plugged in y equals -1. I plugged in x equals 2. I plugged in x equals 2 here. Because it was continuous at that value. We have the same thing going on here for the full function. At this point, if we just plug in 2 for x and -1 for y, this function looks like it's continuous there. If I just plug in, I don't get an indeterminate form like 0 over 0 or infinity over infinity or anything like that. Okay. And each of these on their own is continuous. They're polynomials. And if I divide 2 polynomials, it's still continuous so long as the denominator isn't 0. And the denominator is not going to be 0 at this point. This function, of course, is not continuous at the point 0, 0. We could see that. We'd get 0 over 0 if we plug that point in. Okay? But it is continuous at the point 2, -1. If a function is continuous at a point, then all I need to do to evaluate the limit is plug in the point. I get 4/5. Okay, and that is the answer. The limit does exist and it equals 4/5. This is going to be an important idea going forward. Okay. If f of xy is continuous at x0, y0, then the limit as x comma y approaches x0, y0 of f of xy is just the function value. Okay, and that's what we did here. We said, oh, this is continuous, so we just have to plug the point into the function. That's going to be the limit. If the function is continuous, then you just plug the point into the function and you get the limit. Let's take a look at this example. So for this one, we could, if we wanted, we could look along different paths as we approach 0, 0. And it's a great approach if you think the limit does not exist. If you can find two paths where the limit does not agree, then the full limit does not exist. But for this one, I'm looking at this and I think there is an algebraic technique that we can use to actually evaluate this limit. Okay, I think the limit might exist, but I need to use algebra to show it. So first off, notice right now, if I just plug in 0, 0, I do have an indeterminate form. I would get 0 over 0, right? An indeterminate form like 0 over 0 means we have more work to do. It's not clear what the limit is. It's indeterminate, okay? But I'm looking at this and I notice I could factor the numerator, okay? Specifically, I could use a difference of squares to factor the numerator. Just as a reminder, a difference of squares, if you don't know it, it should be one that you know. This one comes up quite a bit. It's an important one. If I have something squared minus something squared, I can factor it as the two somethings before I square them, and then just swap the signs. Okay, you could check it if you want, FOIL it out. A squared, I get negative AB, I get positive AB, so they cancel, right? The negative AB and the positive AB, and then I get negative B squared, right? So this difference of squares, it's an important one to remember, okay? And I notice that's what I have up here. X to the fourth is x squared squared. Here, let me write it this way. X squared squared. And then 4y to the fourth, that's 2y squared squared. Okay, it's a difference of two squares, which means I can factor them using this difference of squares formula. So if I factor the numerator, I'll get x squared plus 2y squared and x squared minus 2y squared. And I left the denominator as is. Okay? And now with that simplification, I say, okay, wait a second. Now I can use my algebra, cancel out those two. Leaves me with only the numerator. Notice that we got rid of the problem. Now, anywhere close to 0, 0, this and this are equivalent functions. That's what we just said. At 0, 0, they're not the same. Okay? If we were at 0, 0, if x and y both equaled 0, then I'd have 0 here, I'd have 0 here. I can't cancel 0 with 0. But remember, I'm not at 0, 0. X comma y isn't at 0, 0. X comma y is close to 0, 0. And if x and y are close to 0, 0, if they're approaching 0, 0, then that means I can cancel these. Okay? And so for any value where x and y is close to 0, 0, this function and this function have the same value. At 0, 0, they're different, but close to 0, 0, they're the same. And now, this function is continuous at 0, 0. This function isn't, right? If I plug in 0, 0, I get 0 over 0, an indeterminate form. But if I plug 0, 0 in here, I just get 0. I don't get that 0 in the denominator, which means that's the limit. This is our usual strategy for evaluating limits algebraically. We replace something where the limit is undefined, or where we have an indeterminate form. We replace that function with a continuous function. The two functions are equal anywhere where x and y is close to 0, 0, though they may not agree right at 0, 0. And once we have a continuous function, then from what we just saw, all we have to do is plug in to that value, to the function, to get the limit value. Okay. This is because the whole idea of a limit, it's what we're getting close to, right? And the whole idea of continuity is that we can get close to the actual value. So if the function is continuous, then what we're getting close to must be the actual value of the function, right? What we're getting close to must be the actual value of the function if the function is continuous. If it's not continuous, then we could have a hole there or something. But if it's continuous, what we're getting close to has to be the actual value of the function. The function value has to be the limit for a continuous function. Let's take a look at another one. This is another one where I look at it and I think, you know what? Maybe I could use an algebraic technique to find this limit. Now, if I think the limit doesn't exist, I can, of course, start looking along different paths. But in this case, I see that the denominator has a couple square roots in it. I know how to deal with that, I think. Okay? Now, this limit is as xy approaches 0, 0. So the first thing we notice is that the function is not continuous. If I just plug in 0, 0, which is always a good place to start. Know what you're starting with. Plug in your point. Okay? But if I just plug in 0, 0, then I get 0 divided by 0. That would be an indeterminate form. So I have to do some work. Okay? If I can somehow deal with the denominator so I'm no longer dividing by 0, then I should be good to go, right? So I want to somehow re-express this in a way that's going to make it a little easier to work with. I'm going to rationalize the denominator, okay? Now that doesn't guarantee that all of a sudden I'll be able to find the limit, but it often is a good approach, okay? And if at any point I get stuck, I can always go back and start looking along different paths and say, you know what, maybe this limit doesn't exist. But I'm going to rationalize the denominator here. Now, in order to do that, I'm going to want to square this guy, and I'm going to want to square this guy. Notice that's not the same as squaring all of this, right? That I'd have to FOIL it out. I don't want that. I want to square this guy, and I want to square this guy. Where have we seen that before? One guy squared minus another guy squared. Hey, that's a difference of squares, isn't it? So I want to turn this into a difference of squares. And I know that a difference of squares factors is a minus b times a plus b. Okay, so if I want to square each of these guys separately, and right now I have something like this. I have one guy minus another guy. Then I need to multiply by what's called the conjugate. The same two terms, but with the opposite sign in the middle. Okay, so I'm going to multiply by root x, root y, the same two terms, but with the opposite sign in the middle. And of course, what I do at the bottom, I got to keep things balanced, so I'll do the same thing to the top. Okay. So on top, I have the x squared minus xy that was already there. And now I have root x plus root y up there also. Now, I could FOIL this out, couldn't I? Generally, it's good. Things are more useful factored than they are expanded out. So unless I have a good reason, I usually leave things factored. I need to have a real good reason before I multiply them together. Okay, so I'm going to leave this factored. My denominator, though, I do have a good reason for multiplying these two together. Okay, it's the whole reason why I'm multiplying by this in the first place, because I know when I multiply them, I'll get a difference of squares, and I'll be able to get rid of the square roots. Okay, these make a difference of, these will multiply to be a difference of squares. So I'll get the first term squared minus the second term squared. And so I get x squared minus y squared in my denominator. Okay, great. Now I plug in 0, 0, and I still get 0 divided by 0. It's still an indeterminate form. Why did I do all that work? Okay, well, now with x squared minus, I'm sorry, it's not x squared minus y squared, it's x minus y. Right? The square root and the squares cancel. So it's just x, it's just y. Okay? But now, I still get 0 over 0. But now this is a little bit more workable. I can work with this a little bit better. Specifically, if I look at this, remember things are usually better factored than they are multiplied together. So right now, let's take a look at this and let's factor. Okay, specifically, I can factor out an x. So if I pull out an x, that leaves me with x minus y. And then I still got that root x plus root y all over x minus y. Ah, now this is looking promising because now I can cancel these out. Okay, for any xy that's close to 0, 0, x minus y, they'll cancel. Okay, and that was the problem. Right? This term down here, that was giving me my 0 in the denominator. Now I don't even have a denominator. It's gone. So I have replaced my function with a function that is equivalent anywhere close to 0, 0, but continuous at the origin, continuous at 0, 0. Now, if I plug in 0, I don't get an indeterminate form. And so, it's nice and continuous at 0. I could just plug in 0 and get my answer. If I plug in 0, 0, I just get 0. So I was able to algebraically find the limit of this particular function. We have just one more technique to learn in this section. Sometimes we can find the limit of a multivariate function by converting to a different coordinate system. A lot of times it makes things easier. In this case, I'm taking the limit as xy approaches 0, 0 of x natural log of x squared plus y squared. Now, just looking at that as it is, it doesn't look like there's a whole lot algebraically I can do there. Okay? But if I convert to polar coordinates, we'll see that that actually makes things a lot easier. Okay? By the way, just looking at this, polar coordinates might seem like a really good solution because it's going to swap out x squared plus y squared with r squared. And r squared is going to be a lot easier to deal with. A single variable inside that logarithmic function is going to make things a lot easier to work with. Okay? So I'm going to convert to polar coordinates. That means x becomes r times cosine of theta, and natural log of x squared plus y squared becomes natural log of r squared. All right? Now we do have to think, how do we adjust the limit? We're interested in xy approaching 0, 0. So angle theta, that doesn't help us get to 0, 0. That just tells us which direction we're pointing, right? So if we want to go to the origin, all we need to do is we need to make sure the radius goes to 0. Theta isn't going to help us get there. Theta just points us in the direction we want to go. R tells us how far out we are. So if we're going to the origin, we want to get our distance from the origin to go to 0. Okay? Okay. So now what? So I'm going to start off by using a property of logarithms. I get r squared inside the logarithm. Remember, if you have a power inside a log, you can pull it out as a coefficient outside. So I get 2r cosine theta natural log of r. Okay, now notice our limit is only as r approaches 0. Okay, we're only thinking about what's happening as r changes. So in terms of the limit, 2 is certainly a constant, right? So I could pull that out of the limit, but also cosine of theta. Theta is independent of r, so I can think of it as a constant relative to r. I only care about what's happening as r is changing. Cosine theta does not affect the radius at all, nor is it affected by the radius. So it has nothing to do with the limit. So I can pull out both the 2 and the cosine theta from the limit, leaving me just r natural log of r. Okay. This is now calculus 2 style limit. Probably one you've looked at before. How do we approach it though? So a good strategy is first to just plug in 0. If I plug in 0, I'll get 0 here, and natural log of r, as r approaches 0, I'll be getting negative infinity. I realize I just left off something also. I'm saying r is approaching 0. I should really say r is approaching 0 from the right. Positive radius approaching the origin. Okay? If r isn't positive, then I can't just pull out the 2, right? If r is negative, natural log would be undefined. But generally, you only need to worry about the radius as it approaches 0 from the right. Positive radius approaching 0. Okay? As r approaches 0 from the right, natural log of r goes to negative infinity. Okay? Just a quick drawing of the natural log function again, just so you can remember it. So as we approach 0 from the right, we're going down to negative infinity. Okay? 0 times infinity is an indeterminate form, which means we have more work to do. Specifically, what we want to do here is we want to use L'Hopital's rule. But this is not a L'Hopital indeterminate form, right? And a L'Hopital indeterminate form would be 0 over 0 or infinity over infinity. But we can turn this into a L'Hopital indeterminate form with a little bit of work, just a little adjustment. Okay, I'm going to leave natural log of r where it is, but the r in front, I'm actually going to rewrite it as 1 over r in the denominator. Okay, now notice these are equivalent. If I'm dividing by a fraction, I can multiply by the reciprocal. The reciprocal of 1 over r is r, so, they're equivalent. But writing it this way means that if I plug in 0, natural log of r as r approaches 0 from the right is going to negative infinity. And 1 over r, this is natural log of r. Let's draw 1 over r also. Okay, as r approaches 0 from the right, 1 over r goes to positive infinity. And so we get negative infinity over infinity. If we just kind of plug in blindly. That's a L'Hopital indeterminate form. It means I can use L'Hopital's rule. So let's use L'Hopital's rule on that limit. Okay, so I'll take the derivative of the numerator. That's going to be 1 over r. Derivative of the denominator. Derivative of 1 over r, 1 over r is r to the negative 1. So I get negative r to the negative 2, or negative 1 over r squared. Okay, so I just took the derivative of the numerator, derivative of the denominator, according to L'Hopital's rule. Do a little bit of simplification, see what we could do with this now. I'm dividing by 1 over r squared, so I can multiply by the reciprocal. That gives me r squared over r, right? The reciprocal of this gives me the r squared in the numerator, and then this r stays in the denominator. And of course, now I could cancel this r with one of those r's. And that solves my problem, doesn't it? No longer do I have an indeterminate form, as I canceled the r in the denominator, giving me the problems. So that just gives me negative r. Should probably put this in parentheses because of that weird negative out front. So if we take the limit as r goes to 0, that's just 0. And then 0 times whatever this is 0. And so we were able to algebraically find the limit. But the trick again, the big trick, once we get to this point, it's really a calculus 2 problem. The big trick that we're learning here is just this little step here. That's what's new. And that is converting the multivariate function to one using polar coordinates, so we can, because the limit is easier to take using those polar variables. One more example. Let's take a look at this limit here. We want to evaluate this limit by converting to spherical coordinates. Now, this is another one that we look at this in spherical coordinates, even if we weren't told to convert to it. We might look at this and say, gee whiz, spherical coordinates seem like a good idea here, right? Because I've got x squared plus y squared plus z squared not once but twice in this function. Okay. So let's convert to spherical coordinates and see how that helps us out. So every time I see an x squared plus y squared plus z squared, I'll swap it out with a rho squared. So I get the limit of sine of root x squared plus y squared plus z squared becomes square root of rho squared. In the denominator, x squared plus y squared plus z squared is also rho squared. And my limit here, again, for spherical coordinates, my theta, my phi, they're not going to help me get to the origin, right? They just tell me which direction I'm pointing. The rho, the distance from the origin, tells me how to get there. I just have to let that distance go to 0. So I don't have to worry about what theta and phi are doing. I just have to let rho go to 0. And we'll again assume that rho is positive, so we're only approaching 0 from the right side. That will allow us taking the square root without having to worry about any absolute values or anything like that. Okay? So in the numerator, since we're assuming rho is approaching 0 from the right, that means rho will always be positive. Square root of a positive number squared is just the number. Okay, so I get sine of rho over rho. Now, this is actually a limit that you may recognize. This is a calculus 1 limit. It's a classical calculus 1 limit. You would have needed to learn it to be able to derive the derivative of the sine and cosine functions. Okay, but calculus 1 was a long time ago. If you don't remember this, we can use L'Hopital's rule here. If I just plug in 0, sine of 0 is 0 on top, and on bottom, of course, I also get 0. That's a L'Hopital indeterminate form, so I could use L'Hopital's rule. So derivative of sine of rho, cosine. And in the denominator, derivative of rho is just 1. And now I could plug in 0 without any problem, right? Because 1, there's no way 1 will ever become 0. 1 is 1, right? So I no longer have the problem I had before. I'm not going to get a 0 in the denominator. So if I just let rho go to 0, just plug in 0 for cosine function, cosine of 0 is equal to 1. And 1 over 1 is just 1. So the limit here is equal to 1. And we did it by first converting this really nasty looking function to a much nicer looking function using spherical coordinates.